The half-life of bismuth-214 is about 20 minutes. A. Construct a function to model the decay of bismuth-214 over time. Be sure to specify your variables and their units. To get started, let's make a table of values. We'll let T be the time in minutes, and we'll let B of T be the amount of bismuth-214 at a particular time. We're given that the half-life of bismuth-214 is about 20 minutes, so let's increment T by 20 minutes. We're not given how much bismuth-214 we have initially, so we're just going to use the symbol B sub 0 to represent the initial amount. After 20 minutes, we'll have half of the initial amount. The way that we can symbolize that is 1/2 B sub 0. After 40 minutes, we'll have half of a half, which is 1/4 of B sub 0. After 60 minutes, we'll have half of 1/4, which is 1/8 of B sub 0. And to write our function, we want to look for a pattern, and we notice that each value is some number times B sub 0. We have 1/2 times B sub 0. 1/4, which is 1/2 squared times B sub 0, and 1/8, which is 1/2 cubed times B sub 0. So we're going to rewrite each as a power of 1/2 times B sub 0. And now that we've written each quantity as a power of 1/2 times B sub 0, we just have to come up with a relationship between T and the part that's changing, which is the exponent. So how do we connect 0 to 0, 20 to 1, 40 to 2, and 60 to 3? Well, we might notice that 20 divided by 20 is 1, 40 divided by 20 is 2, 60 divided by 20 is 3, and even 0 divided by 20 is 0. So what we need to do is we need to take the value of T and divide it by 20 in order to get the exponent. So that allows us to write our function. We'll have B of T is equal to B sub 0, our initial amount, times a power of 1/2. And in order to get that power of 1/2, we need to take the value of time, T, and divide it by the half-life, which is 20 minutes. So B of T is equal to B sub 0 times 1/2 to the T divided by 20. For part B, it says for any given sample of bismuth-214, how much is left after 1 hour? Well, 1 hour is equal to 60 minutes, and we already see in our table that after 60 minutes we have 1/8 of the original amount. So we could say that there's 1/8 of the original amount, or if we write 1/8 as a decimal, 1/8 is equal to 0.125, which is 12.5%. So we could also say that there's 12.5% of the original amount. Without using the table and using our function from part A, we could just substitute 60 for T. So we would find B of 60 is equal to B sub 0 times 1/2 to the 60 divided by 20. One half to the 60 divided by 20 is 1/2 to the third power, which is 1/8. 1/8 as a decimal is 0.125. So our answer is that we'll have 12.5% of the original amount after 1 hour. Part C, how long will it take to reduce the sample to 25% of its original size? Well, 25% is 25 over 100, which is 1/4. And we can tell from our table that we'll have 1/4 of the original amount after 40 minutes. In other words, if the half-life is 20 minutes, then the quarter life is 40 minutes. So we can just tell from our table that the answer is after 40 minutes. For part D, how long would it take to reduce the sample to 10% of its original size? Well, we've already seen in part B that it takes 1 hour to be reduced to 12.5% of its original size. If another 20 minutes went by, then we would have half of 12.5, which is 6.25. So somewhere between an hour and 20 minutes is how long it will take to reduce the sample to 10% of its original size. But to narrow our time frame down even more, what we could do is to substitute 10% of the original amount for b of t. So we're going to substitute 0.1 times b sub 0 for b of t. And now we just need to solve the equation for t. So let's first of all divide both sides by b sub 0. That gives us 0.1 is equal to 1/2 raised to the t over 20. T is in the exponent, so to solve for t, we can use logarithms. Let's take the logarithm of both sides. I'll use a common logarithm. On the right-hand side, we can use the property of logarithms that says that the logarithm of a power is equal to the exponent of the power times the logarithm of the base. So we'll have logarithm of 0.1 is equal to t over 20 times the logarithm of 1/2. So at this point, in order to solve for t, we just simply need to divide both sides by the logarithm of 1/2 and multiply both sides by 20. So t is equal to 20 times the logarithm of 0.1 divided by the logarithm of 1/2. We can now use a calculator to evaluate the left-hand side, and we get approximately 66 minutes, which is a little bit more than an hour as we expected.